Hello everyone, welcome to my class. Today we are learning curl and divergence. First, quick preview. Both of them describe a flow on a vector field around a point. Curl measures the rotation of the flow in a neighborhood around a point, whereas divergence measures how much flow enters in a neighborhood around a point compared to how much it leaves the neighborhood around that point. Next, we denote and define by the vector differential operator as nabla or del equals to the vectors with component the partial derivatives del over del x, del over del y, del over del z. And the next definitions: let little f be a scalar field and capital F be a vector field with component p, q, r. Then the nabla operator operates with a scalar field which we call a gradient of f, and is defined as it's a vector quantity which is fx, fy, fz. Second, the nabla operator dots with a vector field f, which we call a divergence of f, and is denoted by div f or nabla dot f equals to this scalar quantity, the partial derivative of p with respect to x plus partial derivative of q with respect to y plus partial derivative of r with respect to z. Let me scroll down. Similarly, the nabla operator cross with the vector field, which we call a curl of f, and denoted by curl f, which is nabla cross f. Then we use this determinant to expand this cross product, so which gives us this bunch of partial derivative relations, which you already saw in conservative vector field criterion in our previous classes. So curl f is conservative, then curl f is 0 because these partial derivatives are equal. Let me scroll down. And curl f is 0, then f is conservative provided the domain of f is simply connected. Divergence of f equals to 0 means incompressible, and curl f 0 means irrotational. Great, let's move on. The quick revisit of Green's theorem: we can express the line integrals of vector field as a double integral of curl f dot kta, means vertical component of curl f over d. And then the next one, the normal component of f, which that means the line integrals of f dot n ds over c equals to double integral of divergence of f inside the domain or region d bounded by c. This we do not use in these sections, we use this in the next section, so let me skip for these sections. Let's move on. Some results: divergence of curl f is 0. So quick proof: divergence of curl f is equals to nabla dot nabla cross f, just by the definition. Then this is a scalar triple product among three vectors, so we can switch dot and cross. So this is equals to nabla cross nabla dot f. Then the cross product of the same vectors is 0, so nabla cross nabla 0 means everything 0. Second, curl of gradient f is 0, so which again comes from by the Claudeur's theorem. So by definitions, this is nabla cross gradient f. This is a 3 by 3 determinant. Expand it and use Claudeur's theorem, which gives us 0. And the Laplace operator, just for the introductions here, Laplace operator is denoted by nabla square, which is nabla dot nabla, and Laplace equation is nabla square f equals to 0. But we're not talking about Laplace operator and Laplace equation in these sections or in this class. Okay, so let's move on. Now let's do example. let's compute curl F and divergence of F. So let given vector field is F equals to with component x, y, e, z, comma 0, comma y, z, ex. Then compute curl F. So by definitions, curl F is nabla cross F, which is this 3 by 3 determinant. Expand this determinant, that what we did in chapter 12. Then this is simply the vector given here. Similarly, B, divergence of F, by definitions, nabla dot F. So then take the partial derivative of the first component with respect to x plus partial derivative of second component of F, means the vector field component, with respect to y, plus partial derivative of the third component of vector field with respect to z. Then this gives us y e to the z plus y e to the x. Great. Let's move on. Example 2. So given vector field is x square, y square, z square. Compute the curl of F, again by routine computations, which gives us a 0. Let me check here. The first component of this is this one, del z square over del y, so 0, minus del y square over del z, 0. Last component, del y square over del x is 0, del x square over del y is 0. Awesome. So then we call F is irrotational. B, given vector field is y square z square, comma z square x square, comma x square y square. Compute the divergence of F. So by definitions, divergence of F equals to nabla dot F. So this is the nabla vector, this is the F vector. Take a dot product. How we take a dot product? We multiply the corresponding component and add them. So del y square z square del x is 0, plus del z square x square over del y is 0, del x square y square over del z is 0, so 0. Then we call F is incompressible. Great. Example 3. Determine whether or not the vector field F, where F is 1 sine z, y cosine z, it's a vector, is conservative. So here we show curl F 0 and domain of F is simply connected. So let's first find the curl F. So curl F by definitions, nabla cross F, and by definitions this 3 by 3 determinant, then which gives us 0 vector. Let me check here. So the first component, the partial derivative of y cosine z with respect to y is simply cosine z, minus partial derivative of sine z with respect to del z is cosine z, so cosine z minus cosine z 0. What's the last component? Partial derivative of sine z with respect to x, 0. Partial derivative of 1 with respect to y is 0. So this is 0 vector. And also the domain of F is R cubed, R3, which is open and simply connected. Hence, given vector field is conservative. So we finish these sections. So in the next section we study the flux, the surface integrals. Thank you.